Hi, welcome to PyData Global 2020. Let's just jump right into it. Before I start, all the code and slides you're going to see are available on GitHub, so you're welcome to peruse them anytime at your own leisure. You can change some of the values and run your own optimizations that you're going to see in a second. So it's all here for you to have fun with. What we're going to get into, though, is the slides themselves, and we're going to talk about supercharging decision-making with Bayes' theorem. So who am I? My name is Ravin Kumar. I'm either a data scientist or supply chain engineer or Bayesian statistician, depending on who's asking. I'm a core contributor to PyMC and RVs. Both of these are NumFOCUS sponsored, so I want to thank NumFOCUS for their stewardship of scientific open source software, and of course, for helping put on all the PyDatas, including PyData Global. What I used to do was build supply chain systems for things like these drill ships. I would help figure out when the material needed to be at a certain place, at a certain time, and what people needed to be there to build things like this giant drill ship. I did a very similar thing at SpaceX. I would help plan out when every rocket launch for SpaceX would occur for a number of years. And then I did a similar thing at Sweetgreen, but this time helping figure out how many people we needed in different locations and what ingredients to get everyone the custom salad that they wanted to have. What I do now is I'm a principal data scientist and co-founder at PyMC Labs. PyMC Labs is a consultancy where we help organizations sort of supercharge their decision-making or their models or whatever it may be with Bayesian statistics. And why Bayesian statistics? Well, it turns out it's a pretty useful and powerful algorithm. It can do a lot of things. It can characterize outcomes. So if the outcomes we care about are the weight of all men in California, well, Bayesian statistics can help you understand that. Bayesian statistics can do latent factor analysis. So it helps you understand whether age or smoking or diet, how they affect the outcome of men's weight in California or Texas or China or wherever. We're not going to talk about either of those two things, even though they're powerful on their own. What we're going to talk about is how you can use Bayes' theorems to make decisions. And so every organization needs to make decisions. Whether I was at SpaceX or NOV, we had to make choices about what to buy, when to buy, which suppliers to keep, and we wanted to make the right ones. Typically, human experience is where most people use to make their decisions. When you are with your friends and you want to get lunch, you use human experience to figure out where the best place is to get lunch. But you can also use data to figure out what choices you have and how to make this decision. Each choice is tied to an expected outcome. So we take a choice, and given our experience or what data we have, we tend to have an estimate of what will happen. But what actually happens is related to, but not exactly what you expect, right? If everything you expected to happen actually happened, life would be a lot better, but unfortunately that's not always the case. What we want to do though, and this is the real trick, is we want to make the choice that leads to the best actual outcome. The expected outcome is great, but we really want the best thing to happen. And this is where human experience and data can both be combined to get us. If we just take human experience, the years of experience moniker you hear largely helps bring these two things closer together. As you get more experience with driving your car, or more experience programming, or more experience snowboarding, or pick any activity, you get better at expecting what's going to happen, and what your expectation is ends up being what actually happens. When you're very new, you expect to, so let's say, not fall on your butt when you're snowboarding. But that's what actually happens because you don't quite know what you're doing yet. It's sort of the same thing with machine learning algorithms. When you don't have a lot of data, it's hard for a machine learning algorithm or statistics function to figure out exactly what's going to happen. But as you get more and more data, hopefully the algorithm can come together. And ideally, you can use both of these things to narrow down to the best actual outcome every time. And that's what we want to do with Bayesian statistics. Bayesian statistics is a mathematical formula primarily, but I think more importantly, it's a methodology that helps you characterize that uncertainty. Bayesian statistics is powerful in a particular way because it tends to be able to use small amounts of data. It can leverage small amounts of data and provide uncertainty to help you make better decisions where a lot of other algorithms are unable to do so. So rather than talk about it at a philosophical level, let's dive into a specific example. Anisha is a newspaper vendor now. She, let's say, lives in Los Angeles, where I live. And what she wants to do is buy newspapers in the morning from the Los Angeles Times, and she wants to sell them later at night later in the day to folks in the Los Angeles community. She can buy the newspapers wholesale for $5 and she can sell them for $7. The newspapers only last one day. If she buys the newspapers on Monday, she can't really sell them on Tuesday because they become worthless. Nobody wants a day old newspaper. Each morning, she has to make a choice of how many she wants to buy. And if she buys too little, she loses a bunch of sales. If she buys too many, she wastes the opportunity on unsold papers. So we want to make sure she buys the right amount of newspapers to maximize her profit. How can Anisha get the best outcome? Well, this problem is a well-studied operations research problem called the news vendor problem. It's also called the single period model because the inventory only lasts a single period. In this particular case, the period is one day. So let's first talk about how to calculate the profit. If we know the price Anisha buys the newspaper for, and we know the price that she sells the newspaper for, and we know the demand, and we know the decision, which is how many newspapers she decided to buy, we can use those to calculate Anisha's profit. I want to note that in the simplest version of this problem, we don't account for the sales she didn't make. We only account for the transactions that did occur. So putting sort of numbers to paper, or in this case, numbers to notebook, Jupyter Notebook, we have our newspaper cost for Anisha here. We have the customer price here. We have the choice Anisha made in the morning, which was to buy 42 newspapers. And we're going to assume that demand is fixed at 40 newspapers. We know exactly 40 people want to buy newspapers. What we get here is we have the demand times the customer price is the revenue. This is how much money Anisha has coming into her business. And then newspaper cost times the amount of inventory she holds. This is her inventory cost. And this is how much money is leaving her business, how much money she paid for the newspapers. And in this case, she makes $70 worth of profit. Let's say Anisha then decides to buy 38 newspapers the next day. And we're going to say demand is still fixed at 40 newspapers. In this case, we run the same calculation, but in this case, Anisha sells out her inventory. So we get 38 times the price of 7. This is her revenue again. And then we subtract out her inventory cost. And in this case, she actually made more money, which is interesting. Might be surprising, but she made more money because she didn't lose any money on unsold inventory. Because we're going to do that calculation over and over again, we're going to turn this into a function. And this is everything that we saw before, just in a Python function. We have 42, which is Anisha's choice of inventory, how many she decided to buy. 40 is our demand. We have the same thing over here. 38 is Anisha's choice of inventory, and 40 is the demand. And here is your profit in either scenario. Because this is PyData, somebody would yell at me because there's an obvious one-liner here. And so we've taken that last function and we've turned it into a handy one-line function right here. The numbers are exactly the same. We can now use this function to test out what Anisha's profit would be at every possible inventory choice from 0 to 100. And so here's what the curve looks like. If Anisha buys 0 newspapers, she's going to make $0. Not surprising. As she buys more and more newspapers, she makes $2 per each sale because she buys them for $5 and she sells them for $7. So she keeps making a nice profit all the way up until she gets to 40. And then there's a drop off because for every additional newspaper Anisha buys over 40, she loses $5 because she has inventory that she bought, but she couldn't sell. And if we get to 80 or 90 newspapers, she starts losing a lot of money. So the obvious thing to do, buy 40 newspapers. There's no data science or any sort of magic needed, really. Not even so much math, to be quite honest. You just know that if 40 people want to buy newspapers, you buy exactly 40 newspapers in the morning yourself. But we just want to make sure that this is the right choice. So let's use our SciPy optimizer just to double check. What we do is we define a thing called an objective function. This is what the optimizer will use to as the objective to minimize. Now, the minimization might be a little bit confusing, but that's just a convention. We want to maximize Anisha's profit. So we take the sum of the daily inventory values for all the demands that we have in particular, and we just make it a negative. So it turns into something that the SciPy algorithm will minimize instead. So here's what an optimizer run looks like. I want to point out that this optimizer function can take multiple days of demand. So we've put 40 in here twice. So day 1 and day 2. And we've said that the choices the optimizer can make are anywhere between 0 to buying an infinite amount of newspapers. and we give it the objective function to plug a bunch of numbers into and try and minimize our objective function value. So we see here the optimizer tries a value of 0 and it gets an objective value of 0. It tries a value of 1, it gets an objective value of -4. Then it tries a value of, let's say, 178, and it gets an objective function value of 1,300. This is not good. We don't want higher numbers. So it then goes back on the other extreme to 2 and gets a number of -10. And then after bouncing back and forth, converges on a particular minimization that unsurprisingly ends up at 40. The same answer we had before the optimizer and the obvious answer. I want to point out that these numbers don't mean anything by themselves. They just mean something in relation to another number from the objective function. So it just tells us, given our inventory choice and given the demand, what is a better choice versus another. And in this case, a value of 159 from the objective function for an inventory value of close to 40 is much better than Anisha buying 180 newspapers, losing a bunch of money for what would amount to 130 newspapers unsold. And you can correspondingly see that with a very high objective function number relative to 159. But what if demand is variable? I think you will appreciate that exactly 40 people don't buy newspapers each day. So what do we do when things are variable? So what we're going to do is we're going to run a little bit of a simulation here. We're going to simulate 15 days worth of demand, and we're going to simulate it from a random normal that's characterized with a mean of 40 and a standard deviation of 20. And we're going to take the first 5 days and say Anisha has seen these values. So she's been in the business for 5 days now. She's seen that 75 people wanted newspapers, 48, 85, 77, 60. So she's getting some sense of what people in Los Angeles, how many people in Los Angeles want to buy newspapers. What she hasn't seen yet is the next 10 days worth of demand. So if she's seen these 5 days worth of demand, how can she make the best possible choice for the next 10 days worth of demand? So what most people do, and what most businesses do, is they use the mean of the observed data. We take the average, we say, hey, we'll just take the average, that's what we're going to stock, and that's what we're going to do. So Anisha does that. She takes the average. She says, 69 newspapers on average are sold in the last 5 days, or there's demand for 69 newspapers on average in the last 5 days. So let me just stock 69. We're going to plug that into our objective function, and we see that we get a score of 230. Awesome. This is great. We've actually used data to make a choice, which is commendable, to be quite honest. Unfortunately, though, we could have done a little bit better. We left some information on the table. We didn't use uncertainty anywhere in our decision, and we didn't use the profit or customer information anywhere at all. We didn't point out that Anisha makes $2 in every sale, but could lose $5 for every piece of unsold inventory. It's an asymmetric value for her if she does one versus the other. What does 230 mean? Like I said before, nothing. In this particular case, because that's by itself, but it is going to mean something when we compare it to our next methodology, which is the one we're going to use to address uncertainty. So statistical distributions are a way to help us characterize uncertainty. So let's try it out. So in classical research, you're going to see this thing called the critical fractal equation. What it assumes that if you know the mean and standard deviation or the parameters of your demand distribution, the true parameters of your demand distribution, you get the optimal answer guaranteed. And for a normal distribution, this is what it looks like. You plug in your profit and your loss, your cost to your customer and your cost to your business. You plug in the mean and the standard deviation, and you get a particular number. In this case, on Wikipedia, this is the example they have. But where do we actually get the mean and standard deviation from? We don't have like a magic table or book or source API that'll just give us the true mean and the true standard deviation. Nobody knows that in real life. What we can do though is we've seen 5 data points. So let's take the mean of the demand we've seen, the average of the demand we've seen. Let's take the standard deviation. The average is the same, 69 as before, nothing's different here. But the standard deviation is now 13.2. Okay, this is great. Given that we have the mean and the standard deviation, we can plug this into the critical fractal equation, and then we can use our objective function to see how we did. The critical fractal equation tells us to buy 62 newspapers, less than the ones previously that we did with the average methodology. And given that, and given the next 10 days of demand, we get a score of -92, where lower, again, is better. This is great. We actually moved down from 230 to -92 in our objective function. This time we took more data into account. We took uncertainty using a normal distribution. We used the standard deviation to characterize that uncertainty, and we took into the cost of overstocking versus understocking. This is the graphical representation of just that. Again, we have 5 data points. We got the mean and the standard deviation, what's called the empirical mean and the empirical standard deviation from the data points we have. This gives us a distribution of what we expect newspaper demand to be, making an assumption that it's normal. We plug that into the critical fractal equation, which gives us the optimal answer, and we get 62 newspapers. But given 5 data points, how sure are we that the observed mean and the observed standard deviation are the true mean and the true standard deviation? And the truth is, we actually don't know. We can show this with simulation. We take a standard normal from using the SciPy statistics function or statistics module, and we take 5 random draws from a normal distribution 100 times. And what we do is we take the mean and the standard deviation. And what you can see is depending on which 5 samples you get, even if they're from the same original distribution, the observed mean and the observed standard deviation can vary quite wildly. This dashed line is the true mean. This dashed line is the true standard deviation. And you see that doesn't really line up at any point to be exactly the same as what the true mean and true standard deviation are. And so this is where Bayesian statistics come in. Bayesian statistics is a little bit different. It treats the data as what's fixed, and it treats the parameters as what's unknown. And what we have here is a full Bayesian model for our problem. In a full Bayesian model, you have these things called priors. These are your prior beliefs in the distribution of the parameters, not the distribution of newspaper sales, the distribution of the parameters that characterize newspaper sales. And what we have here is the likelihood. And the likelihood characterizes the observed thing that we see. And the observations here is newspaper demand. And so this is a truncated normal because we can't sell less than 0 newspapers. So we take into account that negative newspaper sales are not possible. And we say we have this prior belief of the newspaper of the mean and the standard deviation of this truncated normal. These 3 blocks here are sort of our instructions to our probabilistic programming language, our framework, in this case PyMC3, that's telling it to draw samples to get our posterior distribution. We'll talk about what posterior means here in a second. And then the posterior predicted distribution of newspaper sales. Again, we'll talk about this in a second. This line here in Arby's is just a function that packages the data together in a nice way. So think of it just like as a data frame for Bayesian statistics. You'll see some outputs from our probabilistic programming language. We won't talk too much about them in this particular talk, but what it's doing is it's using a combination of our priors and our model definition and the data that we've seen, which is the seen demand right here, and it's coming up with a posterior distribution. And so here is the pictures of our posterior distribution. After we take into account our model and our priors, which is our belief in the parameters, and condition those on data, which means feed the model and the probabilistic programming language the data we've seen, we get this range of what we think the mean newspaper's demand could be. The model tends to think that 69 is the most likely value. Unsurprising, again, you saw that 69 was the thing that we got in the previous 2 methodologies, but we also see that 57 could occur, or 81, where you have this range here of the possible mean of demand. We also have a range of the possible the possible distribution of the possible distribution of the standard deviation of newspaper demand. Again, the mean, the most likely value is what we saw, which is 14, but it could range anywhere from 7.9 to 22. And because we have distributions of our parameters, that actually means we have many different distributions of our newspaper estimates. So the Bayesian statistics is telling us that we could have a distribution of newspaper demand that is this one, somewhere around 80 and very narrow, or it could be this green one, which has a mean somewhere around 60 and is very wide. We don't quite know whether it's this one or this one, but we get estimates for both. And what we can do there is we can take all of our estimates for every distribution and take weighted samples to generate a posterior predictive distribution. So we can say, hey, we're probably going to sell around 60 newspapers for sure, but 130 or 20 could actually occur as well. This is giving us, to repeat, estimates of every possible version of the future, not just one possible version of the future. I know these are a lot of distributions. So what I'm going to do is I'm going to recap them all on this slide. The Bayesian statistics lets us characterize, using human experience, the prior distributions before we have any data about what newspaper demand could be from what we observed, what we think before we've seen the data. It lets us characterize what we think the distribution of newspaper demand. So in this case, we think the distribution is a truncated normal. We use inference to get our posterior distributions, which means combine our model, our priors, and our priors to get mathematical estimates using data of what the distribution of the mean and standard deviation could be. This gives us multiple possible distributions of future demand. And then we use all these possible versions of future demand to generate what's called a posterior predictive to really estimate what will actual newspaper demand be. I know it's quite a mouthful. So let's actually see our results first. We're going to take our posterior predictive and we're going to use our optimizer to optimize and figure out what the best version of our inventory holding cost should be, our inventory choice to be. So we take our Bayesian demand estimates, which is what we think is going to happen. We give this to our optimizer just as we have before. And our optimizer tells us to buy 61 newspapers. It's telling us that given what our model is giving us, that 61 really is the best value to purchase in the morning to maximize profit. We're gonna run this through our objective function to see what the score will be. And we see the score here is negative 125, where lower is better. And this is the best score we've had so far. Oops, let me fix this real quick. The optimizer can change a little bit, but 125 is still the best that we've seen. We've used all the information we had in before, but we've also incorporated prior business knowledge, and we've preserved the uncertainty from our smaller data size. We'll talk about this in just a second. By utilizing everything, including human experience and the uncertainty from the smaller data size, we're able to maximize the chances that we get the best particular outcome. Here it is in graphical form, again, because it's quite a lot. We have our priors, which is what we believe in before we've seen any data. We have our observed daily demand. We use both of these in a model to get our posterior estimates of demand. From here, we end up with multiple versions of possible demand of newspapers. Using all of these, literally thousands of them, we can generate a single posterior predictive distribution of newspaper demand, which gets us, again, estimates in every possible version of the future. We can then optimize over every possible version of the future and get what is the best answer of the bunch. And here's the comparison. When we just use the mean, which uses very little information, we get an answer. It's not terrible, but we get one. If we take into account some uncertainty and make some assumptions, we get another answer, which is negative 92, comparatively better. And if we use the Bayesian method, which incorporates human experience and preserves the uncertainty from a small data set, we get the best answer yet. So are there other reasons to use Bayes, though, besides just that I've shown you this one example that it tends to do the best? Well, I'm really glad you asked. There's the two reasons we've already talked about are preservation of uncertainty with small data sets. When you take the mean and the standard deviation, it doesn't matter whether from a distribution from samples, it doesn't really matter whether you have 5 or you have 5,000. You end up with one mean and you end up with one standard deviation, and it removes the uncertainty that comes from a smaller data set. I think intuitively people understand when you've seen 5,000 data sets, you can be more certain about your characterization of the world than when you've seen just 5. And the nice thing about Bayesian statistics is that it handles this type of uncertainty natively. It tends to just quote unquote know that with a lower amount of data to believe the prior is a little bit more, and with a large amount of data, it tends to know to believe the data a little bit more. Another nice thing about Bayesian statistics is it's the distribution flexibility. Not everything in the world is a symmetric normal. You saw that we were able to use a truncated normal, but it probably turns out, and this is my experience in real life, that there oftentimes, is a mean and a sort of bell curve, but there's a really long tail of possible probabilities, possible outcomes. Bayesian statistics is nice because it can handle this non-symmetric newspaper demand and what's called tail risk pretty easily. You don't have to rederive any formulas. You just plug in a likelihood or distributions that look like this instead. I think the biggest thing though is the news vendor model is very simplified, which is why the critical fractal equation is so simple. It makes so many assumptions that the purchase price is fixed, that the demand is stationary, that nothing is changing over time, that it's single period. But if you take any one of those and you break those assumptions, the critical fractal equation no longer applies. So if we assume that newspaper demand varies on weekends, or that it's increasing linearly over time as the population of Los Angeles grows, or that Anisha will get 20 orders every day, or that there's actually 3 different types of people that can order: professionals, companies, and students, or that when Anisha buys 40 newspapers, 5 of them actually might be garbage, they're misprints or have blank pages, she needs to get rid of them, which is called supply side variability. If we have any of these conditions, well, we can't really use the critical fractal equation anymore, but we can extend our Bayesian model quite easily. So for me, it's made it quite easy to extend simple models into more complex ones that fits the complexity of the real world. So we talked about model extensibility and flexibility in one way, but it also is extensible and flexible in model architecture, specifically the model architecture. We can do regressions, we can use advanced architectures like Gaussian processes or autoregressive models or space-based models. An example of this is the Profit Library. It's one of the most popular sort of packaged Bayesian models that does a really good job of time series estimates. And it does this by adding in components for seasonality in months or days or whatever may exist in your demand trend. Bayesian models also have the ability to share data across groups. So with the critical fractal equations, you have to, if let's say I had a newspaper business in New York and a newspaper business in Los Angeles, they're not quite exactly the same, but with the critical fractal equation, you can't share any data across the 2 cities, even though they're kind of the same, even though not exactly the same. With Bayesian models, you have this architecture called multi-level modeling, which lets you share parameters across different, across different cities. And in this case, you can leverage small data sets even more strongly than you could with other methodologies. And yet another benefit, particularly in industry, is that you can use the human experience in a principled manner. It's hard to go to executives and say, well, none of your experience matters. The model told you this. We haven't considered your experience at all. I tend to find that the people around you tend to have a lot of experience. And if you can code that into the model somehow, and in Bayesian models with priors or in the model architecture, it's quite a good thing to do. Now, the argument people make constantly is that priors are subjective and it ruins the sanctity of math. But I have to point out that even with the critical fractal method, there's so much subjectivity. You have to choose a distribution that you believe is a true distribution. That itself is subjective. A lot of times when you're doing data cleaning, you have to remove outliers, or you have to figure out the time period on which you look back. Both of those choices are subjective. So no matter what kind of statistics you use, there's always some sort of subjectivity. I particularly like with Bayesian statistics, the subjectivity comes right at the front. And I do want to point out, although we won't go into priors, there are ways to pick priors that are not subjective. They're called non-informative priors. So if this worries you, there's a path for you, but picking priors in Bayesian statistics is entirely its own talk. So here's my opinion. I think this will probably cause the most consternation, or maybe I'll get the most tweets or shouts on Twitter, is that I think the Bayesian community as a whole also tends to have a more principled workflow when it comes to handling uncertainty in business situations, in my case, than the frequentist community. I tend to find that when I read texts that are like the critical fractal method, it's largely plug and chug. People force the problem to fit a particular derived model, and that's the way that tutorials and things are written. I find when I joined the Bayesian community, I would instead learn the modeling workflow, and I learned how to build a model that fit my particular situation instead of learning a bunch of models that I have to force upon my particular situation. This is not to say frequentist math is bad or it's wrong or it's not right in any way, but as a person that needs to build bespoke models for bespoke industries like SpaceX, it's good to be able to have the flexibility to build the type of models that I need for my particular situation. And so you might ask, why are methods like critical fractal still around? Well, I mean, they're still incredibly useful. You can see that they're simple and more easily understood. And if you can make the assumptions if you have enough data to characterize the true mean of the true standard deviation, if things are the same month to month and not changing over time, you should definitely use the critical fractal equation. It is guaranteed to get you the optimum. It's way easier to implement. You saw that it was only one line of NumPy code. It wasn't a whole bunch of models and distributions and things like that. It's much simpler to explain to stakeholders, and I would not undervalue easy communication to stakeholders. I think data scientists can get caught up with building complex models and forget that they have to explain these complex models to people that don't do modeling every day. And I would say there's a little bit of historical bias. I mean, the methods have been around longer because the newer Bayesian methods are just newer. They've only maybe MCMC methods and so on have only really been used or be built into I'll say quote unquote practical packages for people like me in the last 20 to 15 years. And critical fractal has been around for a much greater amount of time. So here's when I suggest you use Bayesian methods though, and it's not all the time. Actually, it's to be quite honest, it's not, for me, I maybe use Bayesian methods for 30 to 40% of my problems when I was in SpaceX and other companies like that. I use it when prior business knowledge is really important or it's required. Like people know so much that's not in the data set or it's not in the database that we need to incorporate their knowledge somehow. I do it when there's what's called tail risk, when you have to account for all the possibilities that can happen, not just the one that's the most likely to happen. And I have to do it when I need a flexible model architecture that meets my situation. And I really do it when the decision you're making is a really, really big decision. It does take more work to use the Bayesian methods, but some decisions are make or break. They're multi-millions of dollars. They're irreversible. In some particular cases, those decisions can lead to loss of human life. And in those cases, you really want to be taking care that you're using the methodologies that best fit that situation and can help you plan for every possible outcome. And so let me do a quick recap of what we've done. We've learned to use data to make choices, even when there isn't a ton of data. We've learned profit and loss functions, and at least how to use them in the Bayesian context. Certainly, we've working with uncertainty and how posterior distributions and posterior predictive distributions help you work with uncertainty. And we've shown how to optimize over posterior predictive distributions once we have them. And the bottom line again, some decisions are just so important that you want to be using the most flexible tools that fit that situation. And in those cases, Bayesian methods are just, in my opinion, the best suited for those types of decisions. If you're self-learning, there's a bunch of places you can learn. You can read to get a better sense of all the words and things that I was saying. So we have a lot of docs from the PyMC3 team, but we also have, Richard McElrath wrote Statistical Rethinking. There's Bayesian Method for Hackers book that's free online. And just recently published his Regression and Other Stories by Andrew Gelman. They do a great job of explaining all the things that I just talked about. If you're an organization though, and you're looking to just start using Bayesian statistics immediately, you can hire us at PyMC Labs. This is why we're here. We realize that there are a lot of important decisions being made in a suboptimal way. If organizations had a way to get Bayesians like myself and the others at PyMC Labs involved, now they can. So we're happy to build customized modeling solutions for your situation. We have tons of experience across different industries and academia. And most importantly, and this is something we really value, it supports the open source community, the package, and all of it. So just Google us, you'll find our website. And biggest of all, I want to thank PyData Global. Putting on a conference is quite challenging. So thank you, volunteers, for taking up all the uncertainty of planning a conference, particularly given everything going on, and making this happen. I hope you enjoyed this talk. Thanks again.